Welcome back to the next class of nonlinear optics and its application. In the previous class, we have learned something about the basics of Maxwell's equation and its solution. Today, we will going to learn few more things related to basic optics, and the outline of this topic are these. So, direction of the vector E d k in isotropic medium. So, we know what is electric field, what is magnetic field, and what is the d vector, and k is the propagation constant. So, how these things are related to each other, what is the relative direction to this quantity we need to learn in an isotropic system. Then Poynting vector and energy flow, that is very important, that when we launch an electric field into the system, how the energy is going to flow and what should be the direction of this energy, that we are going to learn. Then intensity of an electromagnetic wave. So, when we launch an electromagnetic wave, the intensity is a very important parameter in nonlinear optics. So, we need to know that how the electric field amplitude and intensity are related to each other. So, we will find an expression for that, and finally, we will introduce what is anisotropic medium. So, this is the introduction of anisotropic. I am not going to say much about anisotropic in this particular lecture, but like to say something about the anisotropic, some introduction. So, let us start. Okay. So, the first topic is direction of electric field vector d and k. So, here we can see that in isotropic medium d and E are parallel to each other. So, d is equal to epsilon E, where epsilon is a scalar. If d and E is parallel, then epsilon has to be a scalar. Now, if d and E are parallel, then I will have a plane wave solution for E. So, E is E0 e to the power I k dot r minus omega t as usual. So, what we will do, that we will expand this, because we are dealing with the direction. So, we will like to expand this E. So, E is expanded, the vector E0 is the amplitude of the system or the electric field. So, this electric field amplitude is a vector quantity. So, I expand this vector quantity into x, y, z, and if I expand this into x, y, z, then it will be E x 0 x, this is the x component, this is the y component, and this is the z component of this vector with the unit vector x, y, z. Also, k dot r is expanded here. So, this is nothing but the expansion of whatever is written here in component wise, Now, we know that grad dot E is equal to 0. So, that is, if there is no free charge, even in the material, if there is no free charge, then we can write that grad dot E is equal to 0. Since in isotropic case, if you remember in the previous class, that was our expression, grad dot D is equal to 0. Now, D and E are parallel. So, I can write that grad dot E is also 0. Now, if this is the case, grad dot E is 0, if this is the case, then I can expand this grad operator in this way. We know that this is the unit vector x, this is the vector operator. So, the operator is in this particular form. It will going to operate over this entire E, which is written this, which is equal to 0. So, that means this d dx, there is a dot sign should be here somewhere. So, this d dx, when having a x component, will be, when we make a dot products, only these things will be there with the exponential term. This is a pure scalar term, so we should not bother about that. So, this will be related to this will be related to this, and these will be related to this with this exponential term. So, when we make this operation, we will have a solution like this. So, let me go back. So, that means when I make a operation over this, then what happened, that the derivative will gives me I k x. So, if I look this, the derivative of del x of this term will give me I k x, derivative with this term will give me I k y, and derivative of del z will give me k z. So, this term will come out, and when this term will come out, I will have a expression which suggests that k x E x plus k y E y plus k z E 0 z is equal to 0. So, that means this quantity is 0, I can write this as in dot product, because k x, k y, k z are the x y z component of k vector, E 0 x, E 0 y, E 0 z are the x y z component of the E vector. So, this equation is nothing but k dot E equal to 0. Now, k dot E equal to 0 means k and E are perpendicular to each other. K dot E equal to 0 means vector k is perpendicular to E. This is the first thing we find, that vector k is perpendicular to E. Now, if k is one direction, say a preferred direction, say z, here is shown that k is moving along z direction, then E is perpendicular to k. So, two preferred direction one can assume x and y. This x and y is the two basis set of the E. So, first we find that the propagation constant and E, they are perpendicular to each other. After that we say that if k is along z direction, then what happened, other two perpendicular directions are there, x and y. So, in any whatever the k we have, if it is in z direction, I will have a perpendicular direction which is in x and y plane in the direction of E, which is in y and x plane. We have a general electric field direction which is perpendicular to k as well as j direction. If that is the case, then what happened, this E can be divided into two parts, one is along this direction x and one is along y direction. Any E can be divided into two basis sets. So, these are the two basis sets which are perpendicular to k. These are essentially two polarizations, we call this two polarization state. So, once k is given to me, then what happened, I can understand that E is perpendicular to the vector k. So, there are infinite amount of possibility that k is perpendicular to E is perpendicular to the k, because E can be anywhere in this y z plane. But if I divide this vector into two preferred direction x and y, I should divide in x and y direction. So, these two we can call the basis set of the electric field. These basis sets are nothing but the polarizations of this. So, E has a polarization in this direction, but I can divide this into two basis set, and these basis sets are the polarization along x and y direction, these two perpendicular direction. Okay. So, the important information here is k and E are perpendicular to each other. Okay. So, one very important thing now we will like to know, I mean, that is what are the meaning of these operators. In the left hand side of this slide, you will find some operators are given. These are the operators, grad, dot, curl and del t are the operators. This is a very useful identity. So, if I operate these over the electric field which is as a plane wave form, then what happened, that this will give me this quantity. So, the meaning is if I operate say grad dot E, where E is this form, then these eventually give us I k dot E. If this is a one dimension, then it should be I k E, but if it is a vector form, this is the form. So, from here I can see that if this is the operator which is operating over k, if k has a plane wave solution, this is equivalent to I k operate over E. So, from here we can say that I k is equivalent to this operator. We will going to use this in several places. So, that is why it is important. In the similar way, if I make a curl operation over that, I will have these things, and if I make a derivative with respect to t of this thing, then what happened? So, let me make a derivative. I am try to make a derivative of this quantity E. Then what happened? If E has this particular form, we have I minus I omega and then E. This minus sign because we have kz minus omega t. So, that means del t operation is equivalent to multiplication of minus of I omega. That is as simple as that. So, after having the knowledge of this operation in terms of k and omega, we will going to use that. So, now direction of the magnetic field we try to find out. So, direction of the magnetic field one can find out by simply the relationship with E and B, which is the third equation of Maxwell's equation. Curl cos E is minus del B del t. E has this form, B has this form, as I mentioned, this is a plane wave form. Now, curl cross E is equivalent to I k cross E. When it is equivalent to I k cross E, so del t B is also equivalent to I omega B, because this operator del t is equivalent to minus omega I omega. So, negative sign. So, that is why this minus term is not here. If that is the case, then we combining these two, we have another equation I k cross E is equal to I omega B. If I remove this I term and rearrange, then B is related to k and electric field E in this equation. This is the final expression of B, where we have the value of V as well as the direction of B. So, direction of B is very important. So, from this equation, so let me erase all these things and then only concentrate on this expression, that B, E and K are related with this. So, that means if K is one direction, E is the perpendicular direction, that is in this direction, this is the direction of E, this is the direction of K, then K cross E in the right hand rule, screw rule, gives me the B in this direction. That means B is perpendicular to both electric field E and the propagation direction K. This is not a very unique result, because it is a very general thing. We know that electric field and magnetic field both are perpendicular to the propagation of the light. So, light is a transverse wave. So, transverse wave means that the light is propagating along one direction, and when the light is propagating along one direction, the electric and magnetic field is perpendicular to that particular direction. In this case, light is propagating along k direction. So, electric and magnetic field are perpendicular to that direction. That is one issue. Second thing, electric field and magnetic field itself perpendicular to each other. Both are perpendicular to k, and E and B again perpendicular to each other. So, that is the interesting thing. So, electric field and magnetic field are perpendicular to each other, and also they are mutually perpendicular to k. So, that means they are forming a system of x y z. That means a coordinate system can be formed with this. Okay. Let us go to the next slide. So, the direction of the energy flow. So, the direction of the energy flow is important, but before that we need to know what is the meaning of Poynting vector. So, Poynting vector is a term as written here that it represent the directional energy flux. The energy transfer per unit energy flux is nothing but the energy transfer per unit area per unit time. So, amount of energy that is passing through per unit area per unit time is called the energy flux. So, obviously, this quantity has some unit and the unit is straightforward omega watt divided by meter square. So, that means the energy propagated per unit time is power and per unit area is the unit of area. So, that is why it is meter square. So, it is power divided by meter square. So, now for non-magnetic system mu is mu 0 and B can be represented as mu 0 H and B and H are parallel. Also in isotropic system E and D vectors are parallel to each other, and here the Poynting vector is represented as S. This is the definition of the Poynting vector. S is a Poynting vector, it is represented as E cross H. Also S can be represented in terms of B by just replacing H. So, this is another form, in many places we have this form also. So, now if I look carefully, the direction of S is E cross B. So, previously we find that if K is one direction, E and B are perpendicular to that. When E and B are perpendicular to that, then E cross B is a vector which should be in the same direction of the key. That means, the Poynting vector and the K vector are in same direction. If I take E cross B and using this right hand screw rule, you will find it is in the same direction of the K. But here I should mention very clearly that this is only true for isotropic system, as shown here. Wavefront and energy are propagating in the same direction when the medium is isotropic. So, the wavefront and the energy is propagating in this particular direction when the system is isotropic in nature. But in anisotropic case, we will find that K and S may not be in same direction. That means, wavefront will propagate in a different direction and energy will propagate in another direction. So, there will be a mismatch, we call it as a walk off. We will discuss in detail, for which we will have a different direction for K and S vector. Okay. Let us go to the next slide, which is very important, that is the intensity of the electromagnetic wave. As I mentioned, the nonlinear optics is entirely based on the intensity, that if the intensity is very high, then only we can excite the nonlinear property. So, we always like to know what is the relationship between the intensity and the applied electric field amplitude. So, here is the treatment. So, intensity I of the wave is the energy flow per unit time. That means, I can write this in this way. This bracket says the time average of that. So, time average of my Poynting vector is represented by the bracket of S. It is nothing but, if I write in a proper way, it should be real part of E cross H, and because of the time average we have a half term here. So, real part, because E and H may be a complex quantity with the complex amplitude, but when I make H star, then we can make it entire thing in a real. So, this is the definition of the intensity, but note that intensity is a quantity which do not have any kind of vector, but here I am using a vector in the right hand side. In principle, there should be a mod sign here, but for the time being I am not using the mod sign, and that the reason is that we need to find out in which direction the intensity will flow. Obviously, it will flow in the direction of k, but that we will going to figure out. Now, H star is B star divided by mu, and then if I write B in terms of E and K, which we have done in our previous calculation, then it should be, so B was, if you remember, B was 1 divided by omega into k cross E. That was the direction of vector B. So, now if I make a B star of that, so we will put a star here and we have to put a star on E here. So, this is used here, this is the thing that we have used here, and then we use this value of H here. So, I become 1 divided by 2, and then mu 0 omega term is sitting here, E is this E cross H star is replaced by this quantity k cross E star. Now, we have A cross B cross C, this is the form we are now having. If this is the case, then I can expand A cross B cross C. We know if we expand A cross B cross C, then we will have, so what is A cross B cross C? It is something like B C A minus C A B. Now, E cross K cross E star, if I do, then B here is E. So, my first term is B here is K. So, my first term is K and C is E star and E. So, if I dot E star and E, it will be mod of E square minus C here is my C here is my E star, and then we will have A dot B, that means K dot E. So, I have a mistake here, here one E star term should be there, be careful, there some E star term should be there, but K dot E is 0. We find that in the previous calculation that K dot E is 0. If K dot E term is 0, then we should not bother about the next term. So, then my expression simply comes out to be I is equal to epsilon E 0 mod of E 0 square, that is amplitude square, 2 mu 0 omega and k. So, now I is a vector, I is an intensity, this is not a vector, but I write this in a vector form to ensure that the energy is propagating along k direction. So, technically this equation is not right, but I just here I just put this S sign here, the vector sign here, so that I can know that in which direction the energy is flowing. The energy is flowing along the k direction, but in the next slide we will remove that and eventually find out what is the expression, what is the final expression. Okay. So, as I mentioned, k denotes here the energy, the vector k denotes that the energy is flowing along the k direction. Now, removing the vector sign and using the relation k equal to omega c n and c equal to d, we have this form. So, I replace k as omega c divided by m. So, when I replace k, then I have omega here and c here. So, this omega is cancelled out and we have c and N sitting here. So, now this is the form in many places people use, but I prefer this the next form. I just do not want this mu 0 sitting here, because mu 0 is associated with magnetic system, but I can remove that and I can use a dielectric system and epsilon 0. So, easily one can do that. So, if I write this half of n and then mu 0. So, mu 0 epsilon 0 is nothing but 1 by c square. So, 1 by mu 0 is replaced by epsilon 0 c square. So, when I replace 1 by mu 0 epsilon 0 c square, 1 c will cancel out. So, n and then I write epsilon 0 c square. In the denominator I have 2 c, and this c will cancel out, and mod of v square is there as usual. So, I have half n epsilon 0 c square. So, that is the expression we have. This is a very important expression. We will going to use this expression in many cases. So, you should remember this expression, and this expression tells us that how the intensity is related to the electric field. Okay. Finally, the anisotropic medium. We will just introduce today what is the anisotropic medium quickly, and in the later class we will discuss in detail that what is anisotropic and what is the consequence of that. So, anisotropic medium, where D and E, the first thing is that in anisotropic medium the physical property is not, it depends on the direction. So, in all the direction the physical properties are not same. So, as a result, what happened, that D and E are not necessarily parallel to each other. Since it is not parallel to each other, we write D is equal to epsilon E, but now my epsilon notation is slightly changed. If you note, I write epsilon bar, double bar. So, this is a notation of a tensor quantity. So, we will going to learn what is the meaning of this tensor quantity and what is that. So, the thing is that D and E are now not related to any scalar relation. So, the relation is more complex. So, you can see that why it is complex. So, now D is equal to epsilon 0 E plus P, where P is a polarization, epsilon 0 is scalar, then E is there, and P is now related to E. So, P we know that this is epsilon 0 chi 1 and E. So, P and E are related to this expression, but if I say D and E are not parallel, that means these quantities are not scalar. This is scalar, but this is not scalar. So, this quantity is not scalar means this is not scalar. If this quantity is not scalar, that means P and E are not in same direction. So, they are not parallel to each other, which is very important. P is not parallel to E. P and E are not in the same direction. If that is the case, then that means Px component will not be equal to Ex component multiplied by some constant. Rather, Px component is related to Ex component, Ey component and Ez component. In the similar way, Py component is related to Ey component, Ex component, Ey component and Ez component, and so as for Z. How it is happening? So, let me go back to the next slide and then probably things will be understood. Here we have a figure, and this figure tells everything, that if I launch the electric field in one direction, and we are saying that P and E are not parallel to each other, that means P will generate in a different direction. So, that means the dipole will arrange not in the direction of E, but in some other direction. If that is the case, then what happened? If I divide these things into component wise, then the x component of this P is generated because of the x y z component of E. So, x component of the P is generated due to the application of the electric field, but the electric field x, y and z all components are involved. So, that is why the equation is written in this particular form, these and these. This is true for z. So, if I divide this x, y and z, so readily this x component is not related to the x component of E, rather x, y, z component is there to form the x component of polarization vector P. So, if I write this entire thing in a general way, then we can write it, and we will going to see that one can write in a matrix form. And now, since it is written in a matrix form, this coefficient, this susceptibility coefficient is now not a scalar quantity, rather this is a vector quantity, or this is a tensor quantity. It is not a vector quantity at all, this is a tensor quantity. So, how this tensor quantity will be related and how these things will going to imply, I mean what is the implication of this tensor quantity, we will going to explain this in our next class. So, today we will just introduce the isotropic system and basic of the anisotropic system. Anisotropic system is very important in our case, and in the next class we will learn more about the anisotropic system. With this note, let me conclude today's class. So, thank you for your attention and see you in the next class.